Hi, everyone, and welcome back to the Threat Briefing podcast. If you listened to our previous episodes, you will recognize today's guest. Kostya Vasilkov is back with a follow-up to his deep dive on Black Basta. Kostya, hi, welcome back.
Hi, Lucy.
So that first episode focused on what we could gather from open source intel, but now we've got something far more valuable, leaked internal chat logs straight from the operators. We're going to unpack how Black Basta actually bypassed security controls, what they said to each other during operations, and how their techniques evolved across multiple ransomware builds. First, Kostya, can you quickly recap what we already knew about the Black Basta process and the TTPs they used?
Sure. So in the previous thread briefing, we did a recap of Black Basta's attack lifecycle from initial access to extortion. We talked about their modus operandi from a researcher perspective. The findings were based on forensics, on dynamic analysis, and reverse engineering. But since then, there has been a huge leak of Black Basta's operators' chat messages. So I guess they didn't have a DLP solution in place. Anyway, the leak gave the entire security industry a window to Black Basta's operation. This gave us a unique opportunity not only to confirm our findings about what they did, but also to get answer about why they did it. So sorry for the analogy, but it is very similar to finding a black box of a crashed aircraft. Sure, aviation experts can get a lot of insights and information based solely on the artifacts which found on the ground, but a black box will provide them with much more details as it has the actual recording of the cockpit. And while going over the chats, it sometimes even felt like eavesdropping because Black Basta, like any other organization, has its own politics, including uh, disagreements, arguments, and even gossip. So it feels kind of weird to actually be the fly on the wall. So um, the leak is huge, and I mean huge. There is a lot of correspondence at each and every step of their modus operandi. They're discussing a lot of stuff and constantly consult with each other. So there is a lot of interesting stuff along the way. But in order to keep this briefing short, we need to narrow down our focus. So we'll focus on the stage right after they deployed the command and control payload, such as a brute throttle or cobalt strike or both of them. So and now they're in a stage when they're trying to move forward, but to do so, they need to evade detection by endpoint security. So they worked in a trial and error approach. If something didn't work, they tried another method and another method. And I must say, I was really surprised by just how many techniques they used. It feels like they took a menu of MITRE TTPs, read it from A to Z, and then just said, yes, I want everything. So as I said, they used a lot of techniques, and we'll narrow down our scope to the following evasion techniques. These techniques are fairly common, and I find them interesting, and they are mentioned in a lot of reports. But what do they actually mean? So some of them are quite low level, but I'll do my best to simplify things as much as possible and explain low level concepts in at a high level. So before we start with the first technique, run DLL, we should first establish a common ground and understand what DLL is. So I know that for many people, hearing DLL instantly reminds them those annoying missing DLL errors, but DLL is actually an acronym of Dynamic Link Library. Uh, it's a file that holds many reusable code functions which can be used by many programs. So a single function from one DLL file can be loaded and used by many programs. Um, it is a crucial part of how programs operate on Windows and how Windows operate by itself. So, for example, let's take the action of writing a file. It's such a routine operation that nearly every program has to do it. So instead of every developer reinventing the wheel and by writing their own code to write a file from scratch, Windows provide this functionality. There is a Windows DLL file with the write file function inside of it. And when a program needs to write a file, it loads this function from the DLL and uses it. Please remember this example with write file function, as we'll return to it later. So a DLL file is somewhat similar to an exe file, but the biggest difference is that DLL, as opposed to exe, can't be executed by its own. It must be loaded by another program to be used. So what happens in a situation when a function from a DLL needs to be executed, but there's no hosting program for it? And as the name implies, this is exactly what Run DLL is designed to do. Run DLL. So Run DLL is a program which acts pretty much as a thin wrapper that loads the function from a DLL file and execute it. A lot of Windows legitimate operations are done using Run DLL. So you'll constantly see Run DLL in your task manager. You can see on the screen the syntax of Run DLL execution. Run DLL 32, then the name of the DLL, and the name of the function. And below it, you can see an example of legitimate use of Run DLL. This is used by Windows to open Printer Manager dialog. On older Windows systems, even deleting the history of Internet Explorer would involve Run DLL. So, and because all of that, for endpoint security agent, it's a bit tricky and challenging to monitor Run DLL. And this is why many attackers abuse Run DLL to execute their malicious code as a function within a DLL file. Basically, they disguise their malicious code as legitimate Run DLL process. So here you can see an actual quote from Black Basta chats. By the way, when you see this white text balloons along the deck, it is a copy paste from their messages. So we can see here that one operator of Black Basta explains to other how to execute their malicious code using Run DLL. Run DLL 32, then the file name and the path, and then the function name. And if you look carefully, you'll see that the name of the function suggests that its purpose is to install hooks, which leads us to the next technique, function hooking. Okay, so function hooking is is a technique used to intercept a function call and then redirect it to another function. In other words, function hooking is like tricking a program to so that when it tries to use a certain function, it will run your function instead. And there are many different types and methods of hooking, but for the sake of this example, we'll just cover the basic concept of function hooking. So let's first take a look at the flow of a regular function call without any hook. So do you remember I asked you to keep in mind the write file function? So let's use it again as an example. So on the left, we see a random application. Part of its code is designed to write a file. So it makes a call to Windows write file function, passing it with all the relevant information like file name, what data to write, etc. And then the function writes the file, and then it returns to the rest of the application's code. Easy peasy lemon squeezy. So now let's see how the flow changes when the function is hooked. Again, on the left, we see a random application. Part of its code is to write a file. So it makes a call to Windows write file function, but this time, instead of writing a file, it redirects it to another function with some custom code. So the hook part is colored in yellow in this diagram. And only when it's done running the custom code, it goes back to writing a file, and then it returns to the rest of the application's code. So two things to note here. Each time this program will try to write a file, it will run the custom code as well. And obviously, it depends on the custom code, but it is practically invisible to the end user. So this technique has plenty of legit uses, but let's focus on one legit use, and let's see how it is used by endpoint security. So instead of custom code, now we have a code that's designed to inspect the file before it actually gets written. So let's say the code designed to calculate the hash of the file that's about to be written, and to check if its hash exists in a database of known malicious files. So each time the application will try to write a file, it will first go through the inspection of the endpoint security. And if the file is benign, the code will allow to write the file and the flow will proceed as usual. But if the file is malicious, it won't allow to write a file, and instead of writing the file, it will redirect it back to the rest of the application's code. Now for the juicy part, how this technique is abused to evade endpoint security. So they hook the same function, but here is the twist. They hook it not to monitor it, but to unhook or disable the inspection by endpoint security. As you see by the flow, it just skips the inspection part. And that way they can write a malicious file without endpoint security inspection. I know it is confusing and complicated, but I hope my explanation was good enough. So let's move on to the next technique, process injection. Process injection is when a program adds code into another running program's process and makes it run the code as if it were its own. So as you can see in my illustration, the injecting program adds XYZ to Explorer, and explorer.exe will execute XYZ. So what is the legit use of this technique? In Windows, processes run in isolated environments like silos, and by default, they don't have access to each other. So, but for some programs, by their nature, they need to have access to other processes. For example, performance monitors, they need access to other processes so they could collect performance statistics from them. Accessibility tools, they may inject themselves into applications to read the text content of that application, button labels, messages, and so on. So this technique allows them to run their code inside the target process. Well, the malicious use case is pretty straightforward here. It's like hiding your bad code inside a normal program, and so it looks harmless while doing something malicious. And as you can see, Black Basta operators are aiming to inject their malicious code into Explorer process. Some endpoint security products are bypassed using this technique. Okay, next technique is safe mode boot. Safe mode is a special way to start Windows with only the essential programs, services, and drivers. So it's mainly used to for troubleshooting problems like, I don't know, crashes, malware, driver issues, and so on. So for example, let's say you installed an application that automatically starts with Windows, but unfortunately it causes the Windows to crash. So now you're stuck in a loop because your Windows starts, then the program starts and crashes the system. So actually you don't have the ability to uninstall it. And safe mode lets you start the Windows without running that application on startup and gives you the chance to uninstall it. Fun fact, safe mode was introduced in Windows 95. Lucy, do you remember that Windows? Did you have a chance to use it?
Yeah, that was a long time ago, but yeah.
Oh, yeah. Yeah, you just remind me how old I am. So the problem with safe mode is that some endpoint security products don't run in this mode. So this allows attackers to abuse safe mode to execute their malicious activities without any inspection. And I was surprised to see that in one incident where Black Basta targeted a healthcare provider, they rebooted all the machines in that organization into safe mode, which obviously disabled critical health-related application and disrupted healthcare services. So when they realized what they done and how much attention this would draw from authorities like the FBI, they got actually really scared and even considered giving the victim the decryptor for free.
That was a chaotic event, yes.
Yep.
So what's your advice then as a security researcher to establish the best defenses, especially when endpoint security fails?
That's a great question, which leads me to my next slide. First of all, as you said, sometimes endpoint security is just not enough. I mean, don't get me wrong. I'm not saying that endpoint security is unnecessary. It is very important and effective. And I read an endless amount of Black Basta's messages where they struggled to evade endpoint security, and it took them a lot of time and effort to bypass those solutions. But in the end, these solutions run on the endpoint, making them visible to the attacker and vulnerable to tampering. And pure NDR, as opposed to endpoint security, doesn't reside on the endpoint. So it's not exposed to tampering. And many of the TTPs used by Black Basta generate suspicious traffic that would be detected by an NDR. My second advice is always educate the employees. Almost all the attacks and breaches start with an innocent employee. Well, not always innocent, but often innocent employee clicking on something they shouldn't. So train your personnel on phishing, social engineering, and other relevant threats.
Thank you, Kostya.
No problem.
So that's a wrap for this episode. The leaked logs gave us something rare, unfiltered access to how attackers actually operate and not just what they leave behind, as Kostya mentioned. If this discussion highlighted some gaps in your current detection strategy, you're not alone. The Vectra AI platform was built to detect the behaviors attackers use when they think no one's watching, beyond the endpoint, as Kostya mentioned, without agents, and before ransomware gets deployed. So if you want to learn more about the Vectra platform and try it yourself, visit Vectra.ai, and don't forget to subscribe to the show for more security insights. And see Kostya again, maybe. See ya.
See you.